Let's start with a reminder for our forgetful friends. People who, for whatever reason, just can't get this straight in their notes or in their head. Bless you. Stop it. Three forces act on this box. The interplay of these three forces decide what the box does. If the box is sliding, then the net force on the box is equal to MA. I don't necessarily know if the box is speeding up or slowing down. I know that there are two horizontal forces that act on the box. There's mg times the sine of theta down the ramp, and there's friction. If friction is greater than mg sine theta, the box is slowing down. If mg sine theta is greater than friction, box is speeding up. That's about it, assuming it's going that way down the ramp. Now, we can go further. We know that if this is kinetic friction, then the net force in the y direction equals 0, suggesting that the normal force will be equal to mg cosine theta. You guys have studied this. So I could ultimately say mg sine theta minus mu mg cosine theta equals ma. Right? Putting in there that friction equals mu times the normal force. All review, right? All first semester, relatively okay physics stuff-ish. Nothing particularly interesting. If you want, I could say, well, the acceleration is g sine theta minus mu g cosine theta. So if there's no friction, that disappears. I just get g sine theta. If there is friction, then a is going to be less than that. It might still accelerate down the ramp, or it might be slowing down. I don't really know. Depends on all those factors. Now, I suspect rolling will be similar to this. But definitely the fastest way down the ramp is if we make it really smooth or make it completely slippery and let anything go down that ramp. It won't matter whether it's a box or if it's round. If it's round and there's no friction, it's still just going to slide down the ramp. Because if it's round, no frictional force there, there's nothing to cause it to roll. But if there is friction, then the friction is going to interact with the object to cause it to roll. Let's put those forces back up for a minute, but now let's be a little more critical about how we draw them. Normal force has to be perpendicular to the surface, which means it must lie along a diameter of a round object. Now, I'm assuming a round object. There are plenty of objects that roll that aren't round. In fact, we're going to see a video of these goofy objects that all roll. They're not round, but they just happen to be shaped in such a way that the net force continues to allow them to go down a ramp. So, round, no big deal, though. We've got gravity. That doesn't look straight down to me. That looks straight down to me. That's definitely acting straight down from the center of the object. But then we have friction. And friction is going to try to keep that red point from moving with respect to the surface. I mean, the point of the wheel touches the point on the ramp and doesn't slide. I think it likely, based on the conditions we just described, suggests that friction is that way. But be careful. Deciding the direction of friction might become a little more complicated, especially when we start considering whether the ball is going up the ramp or down the ramp. If I roll it towards the ramp and it starts to climb the ramp, it might be more difficult to figure out the direction of friction. Let me tell you this at the onset. Nothing about friction here has changed. Friction is still trying to prevent one surface from sliding past another. And if you want to get these kinds of problems right, friction will always oppose the motion of the object. Always, whether it's rolling or not. That's incredibly important in a way you can't fully appreciate yet. But friction will always oppose the direction of motion, whether the object is sliding or not. Now, there is absolutely nothing different about this problem when it comes to the translational parts of motion. Net force still equals ma, which means mg sine theta, still down the ramp, minus friction, still up the ramp, equals ma. That is still true. The shape of the object never contributed to this, and still doesn't. Except this is now the static frictional force, which means I can't make a substitution here to find out how much friction is affecting my problem. Although the normal force is still the same value, this inequality means I don't know what the frictional force is. I just know that it must be less than some maximum. So I can't make a substitution and solve for the acceleration now. I can't predict how the object will behave under these circumstances, unless perhaps I take something else into account. Now, here's where things are going to get a little dicey, where you're not going to be happy. Net torque isn't particularly hard to deal with unless you recognize that you haven't picked a pivot point yet. And I know what you want, but I can't give it to you. You would love to believe that friction is causing this object to have a torque about the outside edge, and that's a frictional force that's causing the object to rotate. It makes perfect sense. Look at the way it's drawn. Doesn't it look like this is going to happen due to friction? And that seems very reasonable, except that's not what's happening. The pivot point should be the point that doesn't move. And what point doesn't move? Not the center. This point doesn't move. That's the point of contact. What's actually happening is the disk is rotating this way around that pivot point for an instant. And then in the very next instant, a new pivot point is created as the shape of the object prevents it from rotating into the incline. That's what's actually happening. Now, truth be told, we can do this problem either way. You could decide to put your pivot at the center. But notice, although there is a rotation there, and that is true, that point is moving. And because that point is moving, it's not a true pivot. Also, if you do that, that doesn't really help us as much as you think. It still means that our torque is based on an unknown force, a force whose size we don't know yet, and can't use this to figure out. So, trust me when I say it's in our best interest to put the pivot point at the actual pivot of the system, the point of contact between the round object and the surface. It adds some complications, but fixes others. For one thing, by putting the pivot there, it explains why the top of the object is traveling twice as fast as the middle of the object. I'm not sure if you noticed that. One of the advantages of using the pivot point at that edge is that we eliminate friction and normal force. They do not cause a torque about this point because they're on the pivot. So the only thing that's causing a torque is gravity. which is the thing that is causing motion in the first place, which is why it's better to do it this way. In fact, if we remember that torque is R times F times the sine of an angle, then we could define our object to have radius, capital R, moment of inertia, I, and mass, M. Those seem like reasonable deductions. So, my torque arm length will be capital R. The force will be mg, because that's causing the torque. I'm looking at this torque arm. I'm not sure you can see that. This torque arm, and then the force acting downwards. And then the sine will be the sine of the angle between mg and the normal force, which just happens to be the angle of the ramp. So the torque about that pivot is Rmg sine theta, where theta represents the angle of the ramp. This has to be equal to, all right, moment of inertia. Let's deal with that first. I, center of mass, plus mr squared. I'm using lowercase m, so let's use lowercase m. Now, here's where I'm going to plug in A over R, because we are saying it's rolling. The condition for rolling is that the linear and angular variables are linked together and synchronized, so I can make that substitution. I have to make that substitution. Now, the first thing I want to point out here, which is not obvious, I have the acceleration of the system in terms of all things I tend to know. M, the mass of the object, radius of the object, inertia and mass. These are all given quantities. I don't have to solve for the friction at all. This tells me explicitly how fast the object will accelerate without knowing anything else. I don't need to know mu. I don't need to know the size of the frictional force or even how much that inequality contributes. Which tells me that the thing that controls how fast this thing gets down the ramp is how fast it rotates. That the torque due to gravity completely controls the rate at which this thing will go down the ramp. We've made one assumption though, and it's an important assumption. We've assumed this spot sticks. This only works if that spot doesn't move. So we are assuming rolling. If there isn't rolling, then none of this works. Now, I would like to do a little algebra on that, but is there any questions to this point? All right, a few pieces of algebra. And you won't understand why I'm going to do this, but it's okay if you don't understand for a minute. I'm going to divide both sides by r, which will get rid of that r here and put an r squared here. And I know that doesn't make a lot of sense to you, but it might in a minute. Next, I'm going to separate out the 1 over r squared and the a, so that I can write this as I divided by r squared plus m times a. Do you follow what I've done? I've just distributed the 1 over r squared inside the parenthesis. And when I do that, it cancels out with one of the terms, but not with the other. But that has to equal mg sine theta. Okay. Now, I think this is neat, but I'm a nerd. Net force equals ma. Mg sine theta is the unbalanced force. The inertia of the object here. It's not just mass. We always said that m stood for inertia. But now we have how the rotational inertia is affecting the linear acceleration. Even if you don't appreciate that, which I can get, just another stupid math class, solve this for A, and you get mg sine theta divided by I over r squared plus m. That doesn't really show you anything. But get in your notes, because I'm about to go off to another screen, because this one looks like gobbledygook. Here's what I want you to see. I'm just going to group that different. We had negative work being done, right? Friction is doing negative work as it slides. If I group it different, do you realize that if there's no inertia, no rotational inertia, this just becomes g sine theta? But anything with rotational inertia will accelerate at a slower acceleration, right? The denominator has to be bigger than the numerator here. This whole thing has to be less than 1. Now, the real question is, does that mean the box that slides with friction gets down first? I don't know. The box that slides with friction has the same base acceleration, without the m, has the same base acceleration, but I have to subtract the contribution from friction. So I can't tell you whether the object that slides gets down there first. I can tell you that the object that rolls doesn't lose any energy. That work is not taken out of the system by friction. You'll notice we have an acceleration here that is all positive numbers. Nothing is doing negative work. In the other example, here, no. So an object that rolls never loses energy due to friction. Work might be done by friction, but it's not taken out of the system. All right, this is the linear acceleration of the system. So now you have kind of a way to put this in here. Please notice, this is the center of mass, moment of inertia. It's likely got r squared in it. And it's all times g sine theta, right? If we think of everything that rolls, a hoop, mr squared, a disc, 1/2 mr squared, a hollow ball, 2/3 mr squared, a solid ball, 2/5 mr squared. Everything that could possibly roll. Do you realize that has nothing to do with the radius of the object? That the first thing that will happen is the radius will cancel out. Next, all that's really happening is this fraction's being put in the problem. So it's whether I'm adding 1m, 1/2 m, 2/3 m, or 2/5 m. All determines the acceleration. The smaller that number, the faster it accelerates. So last year we would have done this qualitatively, but now you can do it numerically. You know, putting 2/5 adds the smallest amount. You must accelerate the fastest. Adding 1 makes the acceleration half of what it would have been. So these aren't small differences, they're huge. The more I can lower the rotational inertia, the faster the object will roll. Think about what that would mean if you're trying to make a faster bicycle or a faster automobile. And there's a lot of energy tied up with rotating things. On the other side of that, we didn't look at it completely, but net force times displacement leads to work and change in kinetic energy. We should expect immediately to talk about net torque times displacement doing work and the potential for a change in rotational kinetic energy. I mean, there's work done here by gravity. But in this case, work's doing two things. There's linear work being done, and there's rotational work being done.